So let's start the session. So this is week 7 of Physico Chemical Processes for Wastewater Treatment. This is offered by NPTEL by Professor VC Srivastav from IIT Roorkee. And I am the TA of this course. I am Vaibhav Kabadwal, a PhD scholar from IIT Madras from the Department of Civil Engineering, and my discipline is Environmental Engineering. So today, the outline of the lecture is filtration, adsorption. So these two topics we will see today. So first we will start with filtration and then we'll understand a little bit about adsorption. So we'll understand what is the head loss across a bed of uniform size particles. So what happens? So this is the, let's say this is the filter and it consists of filter particles, it is filter media. So when water will pass through the filter, because of the surface area of the media will cause some resistance, and this resistance will cause head loss. So the head loss through the media is given by Carbon-Cousins equation. Head loss is given by Carbon-Cousins equation. So head loss, if I denote it as HF, it is given by HF F dash L 1 minus E Vs square divided by EQ G dP. So what are these things? Let's see. So uh, HF is the head loss in meters. HF is the head loss across the bed. The unit will be in meters. N is the depth of filter. E is the porosity of the bed. Vs is filtering velocity. Filtering velocity, it will be flow divided by surface area of the filter. Flow divided by surface area of filter. That is Q by A, and its unit will be meter cube per second. Yeah, correct. G is the acceleration due to gravity, and dP is the diameter of particle in the filter media. Right here, these are the uniform size particles. dP is the die of particles in meter. So, what we have assumed here, we have assumed, I will write it here itself. uniform size particles. So this is the particle. So in that equation, F dash is friction factor. Friction factor, which is related to coefficient of drag. And for laminar region, for the laminar flow, its value will be F dash is equals to 150 1 minus E divided by RE plus 1.75. So during filtration, when flow is laminar, then F dash value will be this much. Okay. So this equation is for uniform size particles. Here we have one more thing. Like first we saw HF. In HF, F dash came from in F dash. There is one more thing, Reynolds number. So the Reynolds number formula is pi rho into density of water, filtering velocity, d is the particle by mu. So phi is nothing but shape factor. The rho w is density of water. It will be in kg per meter cube. And shape factor has no unit. Vs is filtering velocity. Mu is dynamic viscosity. Dynamic viscosity. Its unit is in Pascal second or Newton per meter square second. Let's cross check this unit again. So this is mu and d is the diameter of particle in filter medium. Particle. So phi is the shape factor which we studied in last class. So in general, the phi value will range from 0.75 to 0.85. So what if we have multiple layers, means different size particles? In different layers. This is called non-uniform medium. So in this case, what we can observe, there will be different layers. Suppose D1, D2, D3, the particle. So this is not the depth, this is the particle size. Particle size, depth is x. x, let's say it is depth is x1, x2, x3. So let's say x1 plus x2 plus x3. Let's say if there are more layers will be equal to length, total length of the bed. And these are the different size of particles, d1, d2, d3. So the particle size is not equal, non-uniform medium. So in non-uniform medium, there are different sizes of particles are not equal. So, so what will happen in this case? We introduce a term that is called Xij. So we introduce a term Xij. So what is this Xij? So Xij is nothing but the weight fraction. Weight fraction. So how much is the weight of this in the total fraction? So we'll see like the formula HF is equals to L1 minus E Vs square by E cube G summation of Fij into Xij divided by Dij. So Fij is friction factor, X is the fraction of that part. Because if we see, suppose if I take it as 30%, 30%, 40%, 20%. So area will be same from top. Let's say I'm making it like this. Area will be constant for all three layers. So if area is constant, so this 30%, this is this weight is equals. So this 30% will be Xij, means point 0.3 will be Xij. Uh, this is for first layer. For first layer. And point 0.4 it will be for second layer, and point 0.2 will be for third layer. So this is calculated using sieve analysis. Sieve analysis, if you might have studied in soil or in simply it can be done. I will tell you. So how it can be done? Let's see. So what we will do, we will take all the sample, take all filter material. We will sieve it through different sieves. So the bottom one will be the pan. We will pass it through different sieves. Let's say this is 14, 1.41 mm, 0.84 mm, then 0.71 mm. We will pass the filter material through this. So something will be retained here. So whatever is retained in these two pans will be considered. So this average size of, so it will be, so we will say like this is the average size of the particle between these two sieves. So we will say, let's say retention is here 30% of the total total filtered material. So let's say total filtered material is 100 grams. 100 grams. Sorry, 100 grams is the fil filter weight, and 30 gram retained in between sieve A and B. So for this, between A and B, the average particle size is dp. So for this xij, we will consider it as 0.3. That's it. Likewise, we will do it for different size particles. So 100 grams is the weight of total weight of filter medium. 30 gram is retained in sieve B and passed from sieve A. So for this, the average particle size we are considering it as dp. That will be nothing but average of 0.84 plus 0.71 divided by 2. This will be considered as the average particle size. So now let's see how much we have studied. Let's see. So head loss across the filter bed. So this is the, if this is the filter bed, I have not made other components here. So the filter, so if head loss we need to calculate for the filter bed, we will use Cauchy-Carbon equation. This is given by F dash L1 minus E, filtering velocity to the whole square divided by E cube GdP. So this is the, so in that F dash is friction factor. So friction factor formula is this uh, uh, and in this F dash RE will come. RE is the Reynolds number. Reynolds number formula is given here, and for this for the stratified filter medium, the diameter, so they are present in different layers. They are intermixed, not intermixed. Stratified. So for they have different particle size. They have different particle size, and they may have different depths or different percentage of the fraction. So this we will calculate through sieve analysis, and the head loss through the stratified medium is given by this equation. So we will add it for different layers. Or we will calculate this for different layers because it will be different for different layers. So this is the head loss through stratified filter medium. So now let's see one question. So the clean water at 200, it's 20 degrees Celsius actually. Clean water at 20 degrees Celsius is passed through a bed of uniform sand. Clean water at 20 degrees Celsius is passed through a bed of uniform sand. So its uniform sand means uh, only one medium is there. At filtering velocity of 1.39 10 to the power minus 3 meter per second, the sand grains are 0.4 mm in diameter with shape factor of, so let's keep on writing the data. So uniform sand Uniform sand is given with filtering velocity. Vs is filtering velocity, that is 5 meter per second. Oh, we will not use this data. We will use 1.39 into 10 to the power minus 3 meter per second. The sand grains are in, the sand grains are in 1.4 mm. So I will write it as 0.4 into 10 to the power minus 3 meter. So the shade factor is 0.85. The specific gravity G is 2.65. Depth of bed, so that is L is 0.67 meter. Porosity is defined as E, that will be zero point 0.4. So we need to find the head loss to the bed. So this is given. So data is given. We need to calculate, find, need to find head loss to the bed. This you will calculate. So the head loss formula we know. Head loss formula is, so in this, let's make the analogy. So for finding the head loss, we should know F dash, and to find F dash, we should know RE. Correct? So the formula of RE is phi density of water, filtering velocity, rho Vd by mu. So mu is given to us or not? Mu is not given to us. Let's check. So we'll take the value of mu. So for water at 20 degrees Celsius, we can check the appendix and use these values. Density of water is 998.2 kg per meter cube, and this dynamic viscosity will be 1.002 into 10 to the power minus 3 Newton second per meter square. And now we will calculate Reynolds number. So Reynolds number will be 5. 5 was how much? 0.85. Pi was 0.85. Density of water is 998.2 into filtration velocity was how much? Filtration velocity was 1.39 into 10 to the power minus 3. Vs was 1.39 into 10 to the power minus rho V minus 3 into what was the diameter? Diameter was 0.4 into 10 to the power minus 3. So 0.4 into 10 to the power minus 3 divided by dynamic viscosity. What is dynamic viscosity? It is 1.002 into 10 to the power minus. So we will solve it. How much we will get? So on solving, we'll get it as 0.47. So this 0.47 is less than 1. So Reynolds number less than 1 is laminar flow. Points, yeah, 0.47 is less than 1, so it is laminar flow. So we calculate RE, and then we'll calculate. So RE we have calculated. Now we'll calculate F dash, and then we'll calculate HF. This is the uh, this way we will calculate. So F dash, the formula of F dash is 150 151 minus E by RE plus 1.75. So if you will solve it, 150, 1 minus E how much? E was zero point 0.4 divided by RE was 0.47 plus 1.75. So if you solve it, you will get 150 by this, it will be 193.24. Get F dash as 193.24. Now we need to calculate head loss through the filter. So head loss will be F dash L 1 minus E filtering velocity to the power whole square divided by E cube G d to the diameter of particle. So F dash was how much? F dash was 193.2. Let's write it here. 193.24 into length of or depth of bed was 0.67, velocity was 0.4, and filtering velocity was 1.39 into 10 to the power minus 3. Then it is whole square divided by E cube. E was 0.4, the cube G was 9, G is 9.81, D is 0.4, D is 0.4 into 10 to the power minus 3 meter. So if you solve it, we get head loss of around 60 centimeter or 0.6 meter, or we say it as 60 centimeter. So you can see uh, 0.6 meter, no, 0.6, not 60, it will be 6 centimeter. Point 0.6 into 100 centimeter. It will be 60 centimeter only, correct. So the head loss for what? This 0.67 meter after operation, after operation after operation, the head loss will be 60 centimeter for 67 centimeter filter bed. So this is the question. So this is the solution for the question. Now we will see expansion of filter bed. So During filtration, what will happen? Suppose this is the filter, which consists of media particles. Water is going down. So there will be, so the impurities will entrap, be trapped inside the filter. Impurities will be entrapped. So to remove the impurities, we backwash the filter media. So during backwash, what will happen? The media will expand. Backwash, media will expand. Media will expand. It will be, so it is called backwashing because we are supplying water in the opposite direction. So that's why it's called backwashing. It is not called washing. So the media will expand. The distance between the particles will increase, and the water, because we supply water in opposite direction, the media depth will increase and porosity will also increase, and we supply water, so the impurity will come out, and it will be collected through troughs that I am not writing. So let's see the formula. So the head loss through the uh, expanded bed is given by L1 minus E rho m minus rho w divided by rho w. So here HFB is the head loss required to initiate expansion. Head loss required to initiate expansion. 1 minus E here is fraction of packed bed composed of medium. Fraction of packed bed composed of medium. L is the length of bed. Length of bed before expansion actually. This is length of bed before expansion. Rho m is density of medium. Density of medium. And rho w is density of water. So this is density of water. And the head loss of expanded bed will be same, because so this is the head loss before, this is head loss during backwashing. This is the head loss required to initiate expansion. This is the head loss required to initiate expansion. And head loss after head loss of expanded bed It will be, what will change? LFB. So the length will increase and the porosity will also increase, and these things will remain same. Density of medium, density of water, density of water. So this will remain same. So the head loss to the expanded bed will be changed because of total buoyant weight is constant. Total, we can understand it as total buoyant weight will be constant before the expansion and after the expansion, or we can say like the particle surface area will be same before and after, because the head loss will be due to the particle surface. It doesn't matter the gap is increased. So the particle surface area is same, so the friction will be same, so the head loss will be same before the expansion and after the expansion. So we will equate both the equations. So L1 minus E rho m minus rho w divided by rho w will be equal to LFB 1 minus EFB divided by rho m minus rho w divided by density of water. So this term will be cancelled, and the depth of expanded bed will be L1 minus E divided by 1 minus EFB. So this will be the depth of expanded bed. So EFB, as I already told, is the porosity of fluidized bed. Is the porosity of fluidized bed. And LFB is the depth of fluidized bed. So this EFB, the porosity of fluidized bed, is a function of backwash filtering velocity. If I simply write EFB is VB divided by terminal settling velocity of particle to the power 0.22. So if we increase the backwash velocity, EFB will increase, correct? And if the particle is big, diameter of particle is big, then settling velocity will be more. And if settling velocity is more, then EFB will be less. So here we can conclude that EFB is directly proportional to backwash velocity and inversely proportional to terminal settling velocity of particle. Particle means media particle. Terminal settling velocity of media particle. The units will be in meter per second. Both units should be same. So if we put this EFB value in the previous equation, what we will get? So the depth of fluidized bed will be given as L1 minus E divided by 1 minus VB divided by VT to the power 0.22. Okay, so this is the depth of fluidized bed for uniform size of particles. So if this is stratified, So for stratified bed, the depth of expanded bed will be L1 minus E summation of Xij divided by 1 minus Vb divided by Vt ij to the power 0.22. So we'll calculate this term. Calculate this for different layers. Okay. So now we'll solve one question. So this is the example which we solved previously. This is taken from PV notebook. So the filter medium described in example 4.11, this one, to be expanded. The filter medium described in this to be expanded to the porosity to be expanded to a porosity of 0.7 meters. So E was previously how much? 0.4, I think. So we need EFB will be 0.7 this time. So the filter medium described in example 1 to be expanded to a porosity of 0.7 by hydraulic backwash. Determine the required backwash velocity and resulting expanded depth. So what we need to find out? We need to find the required backwash velocity. Backwash velocity and expanded depth. Expanded depth. So backwash velocity. So we have the formula EFB. EFB is Vs Vb by Vt to the power 0.22. So we have EFB, Vb, we need to calculate Vb, and we'll just first find Vt and then calculate Vb. So this is the procedure we will follow. So to calculate Vt, first assume flow is laminar. For Vt, we'll assume that flow is laminar. Though we know that the flow is not laminar during the backwash. During backwashing, the flow is not laminar, it's turbulent. So, but we'll assume and then we'll see it will come more than one. So Vt will be 9.81 into 265. The formula will be, let me write the formula first. The formula will be G density of medium minus density of water divided by D square divided by 18 mu. So G will be 9.81 into 2650 minus 998.2. So the diameter was how much? 0.4 into 10 to the power minus 3 to the power whole square divided by 18. Mu is 1.002 into 10 to the power minus 3. So after solving this Vt, we will get uh, 0.14. After rounding off, it will be 0.14 meter per second. And then we will calculate Reynolds number. Then why we are calculating Reynolds number is to check whether this assumption we told the flow is laminar, so we are using, so that's why we use the Stokes law. We use Stokes law. So the Reynolds number is 5, density of water, rho, filtering velocity, diameter of particle by mu. 5 was 8.5 given, density was 998.2, filtering velocity was 1.39 10 to the power minus 10 to the power. No, it was filtering velocity. So it will be this much. Pi into 998.2 4 into 10 to the power. This was the velocity. We need to take this velocity. So this is not here filtering velocity because this we are checking for Stokes law. This will be settling velocity here. Rho PPD. So rho V will be 0.14 into 4 into 10 to the power minus 4 here. It will be this much divided by mu will be uh, 1.002 into 10 to the power minus 3. So Reynolds number will come out as 47.4. So this is not so this is not laminar, it is transitional flow. What we will do? We will use opening of drag formula. CD will be 24 divided by I plus 3 divided by under root of RE plus 0.34. So if we put the formula of we put the value of RE, how much is RE? RE is 47.4 plus 3 divided by under root 47.4 plus 0.34. So CD will come out as 1.28. Then we'll use one more formula. Vt square will be 4 by 3 G density of medium or density of particle minus density of water into D divided by CD into density of water. So if we solve it, Vt will come out as 0.08 meter per second. But this is not the final. We'll again check RE and then we'll calculate CD. So we'll calculate RE and we'll check CD. And then we'll again do the same steps until the Vt value will be same 2 times. We will iterate it. So once Vt value will come, we'll put in this formula, that is EFP is equals to Vb by Vt to the power 0.22. So if we put EFB to the power 1 by 0.22 into Vt will be Vv. So we know EFB is how much? 0.7 to the power 1 divided by 0.22 into Vt. What is Vt? Vt we calculated. So on solving we will get 0.07 meter per second. 0.07 meter per second. So we'll get Vb as 1. We need to solve this. So we'll solve this, and then what we need to calculate? LFB, depth of expanded bed. So for this the formula is simple, L1 minus E divided by 1 minus EFB. L was 0.7, 1 minus E was 0.4 earlier. After expansion it became 0.7. So the LFB will be 1.34 meter. That's it. Now we will study adsorption. So what is adsorption means? Why we study all those things? What is adsorption? Why adsorption? What to remove? When to use? So adsorption is used to remove which thing? So adsorption is used to remove dissolved solids. So when adsorption is used, so when to use adsorption? So adsorption is used when dissolved solid concentration is not much, not much high, and it is used as a polishing treatment. It is used as a polishing treatment, and we'll study further. So it is used as a polishing treatment and when TDS is less, and it is not used when TDS is high and like that. So advantage of adsorption. So the advantage is like resource recovery is possible. If we see our biological processes, so resource recovery is most of the time not possible. Like organics are in the form of sludge, and nutrients like nitrogen will be uh, if nitrified and then denitrified, it will be converted to nitrogen gas. So here, if what we can do, nutrient is adsorbed and can be applied on field. So here, provided it is not toxic, provided it is not toxic, so we can recover the nutrients and put it in the field. So if we see the wastewater from metal plating industry or from if the wastewater containing that gold containing wastewater, so gold platinum, so we can absorb the dissolved ions and we can recover those things, those metals. And second advantage is shock loading can be done. So if the initial flow contains 10 milligram per liter, but now it contains 50 milligram per liter, so shock loading it can take shock loading because it is physicochemical process, not biological process. So what is adsorbate and adsorbent? So adsorbate and adsorbent. So adsorbate. So we'll see to with the example. So adsorbate means the pollutant. In simple terms, in our terms, I will say it as pollutant which needs to be separated from a fluid. Adsorbent is solid which will adsorb solid which will absorb the adsorbate over its surface. So this fluid can be liquid, it can be gas or liquid. Properties of adsorbate. So the adsorbate, which means the pollutant. So it is asking what should be the property of adsorbate. So adsorbate should be uh, it should be non-biodegradable, non-biodegradable, and it should be non-volatile. Because if it is biodegradable, we can go for biological processes. And if it is non-volatile, we can go for air stripping. So adsorbate should be non-volatile. Adsorbate should be non-volatile and non-biodegradable. We understood. So we can see like benzene and toluene. So this benzene is volatile. So we can remove it via air stripping. Means both air stripping. What is the fundamental of adsorption? So in adsorption, what happens? Extraction of one phase and concentrated into another phase. So this is, let's say, gas. So if gas has some pollutant, it can be absorbed over this solid phase. And suppose if this is liquid phase, it has some adsorption, it has some pollutant, so it can be absorbed over the solid phase. So there are two things. Two things can happen in adsorption. What are the steps of adsorption? So there are four steps of adsorption. So first one is bulk solution transport. Bulk solution transport. So in bulk solution transport, what will happen? Movement of adsorbate from bulk of the solution to the film surrounding the adsorbate. So first take the example here. Suppose this is the container. I am making a big this is the adsorbate, and these are the adsorbates. So I'm making one layer. So in addition, you saw there is a layer around around the interface. So this is the air. This is the layer film. So bulk diffusion is so first one is film. First one is bulk diffusion. So the pollutant will come from bulk to this near this layer. So this is step one. I will write it here itself. This is step one. So bulk solution transport is movement of adsorbate from the bulk of the solution to the film surrounding the adsorbate. So the adsorbate will come near the film surrounding the adsorbent. So this is step one. Step two is film diffusion transport. Film diffusion transport. So what will happen here? Movement of adsorbate across the external liquid film to the external surface side on the adsorbent particle. So I will make it little bit big. So this is the so it will cross this. So this is step two. It will so this is the film. So it will cross this film. This is step two. And step three, pore transport. Let's say if there is a pore inside, it will go inside. So migration of adsorbate within the pores of the adsorbent by interparticle diffusion. So through interparticle diffusion, suppose let's say if it has pores inside. So it will go inside. So this is third. It will go inside. And fourth point, it will get adsorbed. So third point is migration of adsorbent within the pores of the adsorbent by interparticle diffusion or pore diffusion. And adsorption and last step is adsorption. Adsorption of adsorbate at the internal surface side. These are the steps of adsorption, or we can say sometimes mechanism. This is the mechanism of radiation. So how pores are classified in adsorbent? So we have seen that it has pores. So in different textbooks, different types of uh, uh, in so basically the pores are uh, classified into three. These are macropores, mesopores, and micropores. So macropores are greater than 25 nanometer size. So different books have specified little bit different specifications, but somewhat similar kind of sizes they have given. Mesopore will have 1 to 25 nanometer, and micropore has size less than 1 nanometer. So these pores we can check through scanning electron microscope scope and X-ray diffraction also. So through this we can check the size of pores. So what is adsorption equilibrium? So when rate of adsorption is equal to rate of desorption, this is called adsorption equilibrium. Let's understand this, what is adsorption and what is desorption. So let's say this is the surface, this is the pore. So the this is the adsorbent. Let's make it colorful. This is the adsorbent, so it is coming inside. There are multiple number of adsorbents. Uh, Adsorbent is coming, and simultaneously it will start to leave. So a concentration when rate of adsorption. So in this side adsorb. So in this side adsorption is taking place, and desorption is also taking place. So when both rates will be equal, then it is called equilibrium. How adsorption studies are done. So these studies are done in two ways. One is batch study and one is column study. So in batch study, what we'll do, we'll take the conical flask. We'll take the conical flask and we'll take water and we'll take the water with adsorbate, and we'll put the adsorbent, and then we'll mix it, and then we'll check the time period. Then we'll check a different time period. So this is batch study. In column study, we'll take the column, we'll fill it with adsorbent. We'll fill it with adsorbent, and then we'll pass the water, water or wastewater containing adsorbate, and then we'll through this way the column studies are done. So these are two ways: batch study and column study. Physical and chemical adsorption. So physical adsorption we'll see. The physical adsorption is due to the absorption between the attraction between adsorbent and adsorbate through van der Waals forces. It is due to van der Waals forces. While this physical adsorption, chemical adsorption. So this is due to van der Waals forces, while these van der Waals forces are actually weak forces. So this is due to attraction between adsorbent and adsorbent due to chemical forces. Chemical forces. It occurs at low temperature. It occurs at high temperature. All gases. So almost all gases show this type of adsorption at low temperature. So almost all gases. So this is non-specific. It is not specific, non-specific. So but this chemical adsorption, very few cases show this type of adsorption. So it is very specific in nature. Very few gases. So it is highly specific. So it is reversible in nature because these bonds are weak, so it is reversible in nature. But this chemical adsorption is usually irreversible. Usually irreversible in nature. Usually irreversible. It attains equilibrium. It attains equilibrium. Equilibrium means which we studied in the last slide, adsorption and desorption. It attains equilibrium very rapidly on changing temperature and pressure. On changing temperature and pressure, but this is relatively slower. This is slower. So one more difference is there, but like it forms multi-layer. It forms monolayer. The thing is that so in like these are only weak forces, and they can one can attach over others. But here in chemical, it can't attach because one will be positive, one will be negative. So here they don't have charges here, they are just because of van der Waals forces of attraction. So negative particles can't attract each other. They will repel. So that's why only monolayer is getting formed. So here multiple layers are getting attached. Which one can be removed easily from water? So suppose this is about solute. Sorry, adsorbate. So this is about adsorbate. So hydrophilic, hydrophobic. So we are talking about this question. So which one can be removed easily from water? So adsorbate. So this is about adsorbate. So if adsorbate is hydrophilic, means water loving. So it will not leave water. So it will be in water. And if it is hydrophobic, provided other factors are also same. So hydrophobic will will go away from water and will get absorbed easily. Hydrophobic means water repellent will get absorbed easily, easier will absorb easier than hydrophilic. Factors affecting or controlling adsorption. So these are the factors which affect or control adsorption. So one is nature of adsorbent. Uh, what is the size of pore? Like we studied three types of pores. So in these three categories, which pores are maximum in an adsorbent that matters? What is the shape of the pores? Like we have seen, the shape can be cylindrical, it can be conical, it can be slits in the form of slits, it can be in the form of spherical or ink bottle. So what is the pH of the solution? What is the contact time? What is the initial concentration of the adsorbate? What is the temperature? So all these factors will affect the adsorption. Why kinetic study is performed? So the kinetic study is performed to find the rate of adsorption. Yeah. Kinetic study is performed to understand the rate of adsorption. So on this, we will see it in the next slide. So we'll find the time, or that time is called equilibrium time. So now we'll study about equilibrium study. So in equilibrium study, what we'll do, we'll take the this conical flask, we'll fill it with, it will contain adsorbate and adsorbent both. We'll take multiple. Either so we can either we can take one. I will write here. Either we can take one conical flask, or we can take group of conical flasks. So this I will tell you for one conical flask, and same can be done for multiple conical flasks also. So it will contain, so it has water plus adsorbate, also it has adsorbent. So let's say it will not specify things. So what we will do, at t is equals to 0, we have put the pollutant of concentration C naught, and the volume is V. V is volume of water in flask, and what is this? Uh, M will be the mass of adsorbent. So M will be the mass of adsorbent. Yeah, so we have at T is equals to 0, we have concentration of pollutant or adsorbate C naught, and V is the volume of water in the flask, M is the mass of adsorbent kept in this volumetric flask. So what we will do, at T is equals to 0, the concentration will be C naught, we know, at different time intervals. T is equals to T1, T is equals to T2, T is equals to T3, at different time intervals. We will check the concentration C1, C2, C3, C4. So it will come. So we will check the concentration at different time intervals. So a time interval will come when this concentration will not change. This concentration will be constant. Let's say it will be C4 only. It will not change. So that concentration is yeah. So what we'll do, we'll plot. This is time. Like I told, we'll plot between time and concentration. I should not draw like this. So we'll plot concentration versus time. Initial concentration was C naught. So let's say it is Ct. So it will plot like this: C1, C2, C3, C4. So the concentration will be then C4, 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 C4 only. So this will be C1, C2, C3, C4. So after this time period, the concentration is not changing with time. This time is called equilibrium time. It's called equilibrium time. So now we will do, so same thing can be done. So what we are in this case, what we have done, at different time interval, we are taking the sample from the same volume, from the same flask. So what we can do, same thing we can do, we can take the different number of flasks. We will take at different time interval, we will take different volumetric flask. We'll take different volumetric flask, and you and only once we will take the reading. Only once we will take the reading, and we won't take the reading next, because we will assume like uh, the the sample volume will change and it will be disturbed kind of thing. So what else we can do? So expression for equilibrium, we'll write expression equilibrium. So what we will say, amount adsorbed, amount ad, amount adsorbed on the adsorbent will be equal to the change change in the concentration, change in the concentration of adsorbate, or we can write it as, initial amount of adsorbate minus final amount of adsorbate. So let's say this is the adsorbate. So in this, so that this is the adsorbate. So in this adsorbate, QE is the concentration. So QE will define like this milligram of adsorbate over per gram of adsorbent. So let's say at equilibrium, the concentration over the adsorbate is QE milligram per gram of adsorbent into QE into mass of adsorbent, and V into C naught will be initial concentration, V into C will be final concentration. So the QE will be V by N divided by C naught minus C. This is the expression for adsorbed phase concentration. Now we will see few models. So we will see pseudo first order model. So pseudo first order model is dq by dt is kqe minus q. So after, on solving you will get log qe minus qt equals to log qe minus k divided by 2.303 into t. So if you plot it, if you plot between log qe versus t, you will get the intercept here as log qe. No, it should be plotted between log qe minus qt. Log qe minus qt versus time, and this will be log qe. So and slope will be k divided by 2.303. So this is pseudo first order. So k here it will be first order absorption rate constant. Now we will see. It is also called Lagrange's model. First one. Second one we will see pseudo second order model. Pseudo second order model. So it will be dq by dt will be k qe minus q to the power whole square. So if you solve it, get the equation like t divided by qt equals to 1 by pq square plus 1 by q into t, and we'll plot the graph between t by qt divide versus time. So if we solve it, if we plot the graph, so it will be this intercept will be 1 divided by k qe square, and the slope will be 1 by qe. The third model is interparticle diffusion model. So this model is used when pore transport. So like we have seen pore mechanism. So the third one was pore diffusion. So when pore diffusion is the rate limiting step, then we use this uh, model. When pore diffusion is rate limiting step. So it is written as Qt equals to KID T to the power 0.5 plus CI. So KID is diffusion constant, unit is milligram per gram minute to the power 0.5, and CI is a constant which is directly proportional to the boundary layer thickness. Boundary layer thickness. Proportional CI is the constant. Boundary layer thickness. And if you plot it in the next one. Plot it as Qt versus T under root T. Qt versus under root T. Qt versus under root T. So it will be like this. It will be straight line, and this slope will be KID, and this will be CI. So this was about interparticle diffusion model.